Lesson 30 has two parts. The first part is on working with square roots, and we briefly mentioned square roots back in Lesson 2, and how an entire cult, the Pythagoreans, actually freaked out over the square root of 2. So let's not be like them and freak out about the square root of 2 or square roots themselves. So you do have a new symbol that you need to get used to, and we have this square root symbol. And take a look at that in your rules and definitions, and also that perfect squares chart to memorize. I have that over here to the left. That's something you'll want to memorize. But that square root symbol, that was developed by Leonard Euler in the 1700s as a way to simplify the writing of fractional exponents. Back then in the 1700s, they did pretty much all of their math by hand, and so finding ways to do things faster was very sought after. So this symbol has stood the test of time, and that's what's called the square root symbol, also called the radical sign. And so for any number, x, that actually equals x to the 1/2 power. You've been working with things like x squared or 2 squared or 3 squared. You know how to do those, but we haven't really talked about x to the 1/2 power. That's kind of how you go back to the original number. So if you have 16 in your perfect squares chart down here, if n is 4, then n squared is 4 times 4, right? And 4 times 4 is 16. So how do you go back? If you have 16, how do you go back to n? Well, the square root of 16, that gets you back to 4. That equals 4. So anyways, the Pythagoreans, they put their faith in numbers alone, and that proved to be a really bad idea. But just like all humans, the Pythagoreans, they were created in God's image, right? The fact that they were freaked out by a seemingly simple thing like the square root of 2, though, that should make us stop and consider what problems it might create for us, but also that we don't put our faith in numbers either. So both square roots and perfect squares actually do have something to do with squares. So for example, think about lesson 19. There we talked about the formula for the area of a square, and that's the length of one side times another side, right? So if you had a square and all the sides on a square are the same length, right? If we want to find the area of a square, this area in here, area is just equal to n times n. Or we could simplify that and just say area equals n squared. Sometimes s is used for side. So you might see it s squared. Doesn't matter, it's just a variable. But that's why we call these perfect squares, because it does have something to do with the shape of a square. So these perfect squares, those are values resulting from integer values for s or n if you want to use the variables that we use in this perfect square chart here. So put a good effort into memorizing those perfect squares. Now, unlike some of the results of problems similar to example 19.3, perfect squares, they have no messy fractions or decimals. They're perfect. And if you remember back example 19.3, we did some squares of things, multiplying the same thing twice. But those weren't always perfect squares. Perfect squares, those are these integer values that you see in the chart. So in part 30A here, we'll get used to working with square roots by seeing them in familiar problems like order of operations, which we started back in lesson 22. One of the most important things to remember here is this rule: square root of n squared is equal to n. Okay? So the square root of that perfect square, that gets you back to n. So thinking of squares again, what this says is that the square root of the area of a square equals the side length, s. So for example, using values from the perfect squares chart again, if the area of a square is 64, right here, if its area was 64, what's its side length? Well, its side length is 8, right, over here. Because the square root of 64, The square root of that n squared value, that is 8. If the area was 81, then the length would be 9, right? If the area is 100, the length would be 10 of a side of a square. Okay? In other words, what we're saying there is the square root of 64 is 8. The square root of 81 is 9. The square root of 100 is 10, and so on and so on. Okay? Taking the square root of a perfect square gets you back to the value of n. One final thing about square roots, do you see how taking the square root that cuts the exponent in half? So for example, the perfect square for 8 is 64, right? 8 squared, or 64. So we can write that 64 as 8 squared. Now, what is half of 2? Well, it's 1, of course. When we take the square root, we're cutting the exponent in half, right? So we cut that 2 in half. That gets us back this way, right? Gets us back to 8. 2 over 2 is 1, right? It's understood that 1 is there. We don't have to write it, so we just say 8. So as you learned in the lesson 19 rules, you don't need to write exponents of 1. It's understood the exponent of is 1 if it's not written there. And as your lesson 30 definitions describe, the square root symbol or radical sign is just a simpler way of writing a fractional exponent of half. And so that tells us to cut the exponent in half. So just like half of 2 is 1, the square root of n squared is n to the 1. Do you see the relation there? N, converting that to the perfect square n squared, we divide that by 2 or times it by a half. Okay? If we times it by a half, that gets us back to n to the 1, right? 2 times half, or 2 over 2, is 1. So hopefully you see that cyclical process there. You have a number n, you square it, creating a perfect square. You take the square root of that to get it back to n. Let's do some examples now. Simplify these. So for a, we have the square root of 19 squared. So apply the rule here. Let's just write it over here. Square root, or actually let's just write it for both a and for b. Just because it's new, we want to get it memorized, okay? Now let's write our problem right underneath that. Square root of 19 squared. Do you see how n is 19 now? So this just equals 19. There's our answer, okay? If the square root of n squared is n, then the square root of 19 squared is 19. Same with b. If you get this, obviously you don't need to write this over again, but the rest of your math, you'll have formulas that you use like this, and you're just substituting a number in to that formula, and it's important for you to be able to see the pattern here and recognize the pattern, and that helps you realize that you're not doing something totally different every single time. There's one new thing. We changed the number from 19 to 1. That's all we did, but the pattern's the same, right? The square root of n squared is n. That means the square root of 19 squared is 19, and the square root of 1 squared is 1. The answer, we just cut that exponent in half, 1 to the 1 power, but it's understood there's a 1 there, so we don't write it. Example 2, simplify these perfect squares. Okay, so you were told, unlike in problem 1, you're told these are perfect squares, okay? And so you don't freak out like a Pythagorean because there's no squared symbol inside the square root sign. You make that connection back to perfect squares. So a, there's a couple of ways you could do that. You look for 36 in the perfect squares column over here. Because why are you doing that? Well, because it was told to you that it's a perfect square. So you look for 36. Here's 36. What's the square root of 36? 6. The other way to do it is think about, well, 36 is what squared? Well, it's 6 squared, right? So I could say the square root of 6 squared, that equals 6. Just like the square root of n squared equals n. Okay? B, square root of 144. Where's that? It's a perfect square. We've been told it's a perfect square. It's right down here. So the square root of that is just 12. That's our answer. Okay. Of course, you could rewrite it as the square root of 12 squared, and then you can see based on this rule here that how that equals 12. Problem 3, simplify. So we have an order of operations problem. In lesson 22, you learned about PEMDAS, parentheses, exponents, multiplication, and so on. So parentheses, exponents, those are first, right? So anything that's kind of grouped together is considered parentheses. I mean, absolute value that doesn't have parentheses. It has these vertical bars on the ends, but we treat that like parentheses. Same with the square root. We'll simplify inside there first. Okay? So let's start going then. 4 squared, we'd say that's 16. And then plus absolute value of a negative 3, we can say, minus the square root of 25. Okay, now if you've got your perfect squares memorized already, you know that 25 is a perfect square, right? It's right here. So the square root of a perfect square is n, right? It gets you back to the left, so it's 5, right? So we just say minus 5. Okay, let's keep simplifying. 16 plus absolute value of negative 3 is just the number, right? We're just focused on the number there, so the number is a 3. We don't worry about the sign inside. So we say plus 3 minus 5. Add in pairs, 16 plus 3 is 19, minus 5. 19 minus 5 is 14. So there's our answer. Okay? Memorize your perfect squares chart here. Understand that whatever the n squared column is, you get back to n by taking the square root of that. Square root of 25 is 5. The sooner you memorize that, the faster future math lessons will go for you, guaranteed. Moving on to part B and prime factorization and perfect squares. Look at these different squares. The two on the left, you see how those are perfect squares, and the two on the right are not perfect squares. They're still squares, they're just not perfect squares. Okay? Do you see the difference? Everything about the two squares on the left is perfect, meaning no decimal values, no weird square root values for sides. Like here, square root of 11 are the sides. I mean, the area is nice, it's just 11, but the sides are kind of weird. They got the square root symbols around them. The other one, it's got decimal values for everywhere, so those aren't perfect squares. We mentioned that in part A, but sometimes it just helps to see what we're talking about here. And since this is all about squares, let's put some actual squares on the screen there and take a look at those. Another unique property of perfect squares is they can be factored into prime factors. So values that are not perfect squares, they won't factor into prime factors. So for example, you can't take the square root of 11 and factor that into prime factors, or 5.5. Okay? So let's do some examples to understand this some more. Example 30.4, write the prime factorization of 36 and square root of 36. So you might recall doing prime factorization of a perfect square in example 10.5. And there you learn that prime factors are repeated twice for perfect squares. So therefore the prime factorization of 36, let's just look at 36, that equals 4 times 9. And there's different ways we could break it down first, but let's just break it down like this. 4 is 2 times 2. And then 9 is 3 times 3. So you see how it has the same factor repeated twice, the 2's repeated twice, the 3's repeated twice. Now what about the square root of 36? Well, first take the square root of 36, which hopefully you know that's 6. Hopefully you're catching on here now, and you are using this chart and you know, well, to go this direction, I take the square root of that perfect square. Square root of 36 is 6. Okay? So write the prime factorization of that. It's just 2 times 3. Do you see what happened there? The prime factors are the same for square root of 36. There's just half as many. We cut them in half. Okay? Just like we were saying before, how we cut the exponent in half. The exponent tells us how many times to repeat a factor, right? If we see 3 squared, that means multiplication-wise, we do the 3 2 times, right? The square root of a perfect square, we're cutting that in half. That's what we do when we take the square root. We cut that exponent in half, and so we get half of the number of factors, right? 3 to the 1 is just 3. Okay, well that's all for lesson 30.